Today we will discuss about the basic terminologies used in robots. The first one are the links and the joints. So links are the solid structural members of a robot, and joints are the movable couplings between the links. Okay, like in the human arm, we can say that the shoulder joint is there and elbow joint is there. Okay, and the part between the shoulder joint and the elbow joint, that is the link. Okay, similar in the this is the case with the robots, so links and the joints. So next thing is the degree of freedom. So each joint on the robot introduces a degree of freedom. So each degree of freedom can be a slider, rotary, or other type of actuator. Okay, so their robots they are having usually 5 or 6 degrees of freedom. The usual applications which we encounter. Okay, so 3 degree of freedom allow positioning in 3D space, while the other 2 or 3 degrees of freedom are used for orientation of the end effector. End effector like the fingers in our arms, in our hands, in our palm. Okay, then 6 degrees of freedom are enough to allow the robot to reach all positions and orientations in 3D space. Okay, then 5 degree of freedom requires a restriction to 2D space, okay, or else it limits its orientations. So they are used for handling tools, okay, like the arc welders. So commonly we can say six degrees of freedom are used in normal or the common applications of robots. Okay, then next is the orientation axis. So basically, if the tool is held at a fixed position, the orientation determines which direction it can be pointed in. Okay, roll, pitch, and yaw. They are the common orientation axis used. Okay, we will see here like in the next this diagram. The directions they show the rolling. Okay, then yaw, pitch with in the forward direction. Okay, roll in the up or down. Okay, then next is looking at the figure below, it will be obvious that the tool can be positioned at any orientation in space. Okay, so imagine sitting in a plane. So if the plane rolls you with turn upside down, okay, the pitch changes for takeoff and landing, and when flying in a crosswind, the plane will yaw. Next is the position axis. Okay, so the tool, the regardless of the orientation, the tool or basically the end, the point in the robot. Okay, so that can be moved to a number of positions in space. Various robot geometries are suited to different work geometries. We will see the workspace in our coming slide. So next is the tool center point. Tool center point is located either on the robot or the tool. So typically the tool center point is used when referring to the robot's position as well as the focal point of the tool. Okay, so the tool center point could be the tip of a welding torch. Okay, so the TCB can be specified in Cartesian, cylindrical, spherical, because the different type of coordinates. So as tools are changed, we will often reprogram the robot for the tool center point. Is different tool, then different tool center point. We need to reprogram. So this is the direct diagram which is showing the workspace or the envelope where the robot can perform some desired task. So the robot tends to have a fixed and limited geometry. The work envelope is the boundary of positions in space, and the robot can reach a work in that space. So for Cartesian robot, okay, like a overhead crane, the workspace might be a square, okay, because up and down type of movements are more common. And then in some rotation type, forming a square. Okay, for more sophisticated robot, the workspace might be a shape that looks like a clump of intersecting bubbles. So speed. So, one of the major advantages of the robot is its high speed. So speed refers either to the maximum velocity that is achievable by the TCP or by the individual joints. This number is not accurate in most robots and will vary over the workspace as the geometry of the robot changes. The number will often reflect the maximum safest speed possible. So some robots allow the maximum rated speed to be passed, but it should be done with great care. Okay, means the speed we should monitor. Okay, next is the payload. The payload indicates the maximum mass of the robot can lift before either failure of the robot or dramatic loss of accuracy. Means how much load, the loading capability of the robot. Because it is possible to exceed the maximum payload and still have the robot operate, but this is not usually practiced because there the quality or the accuracy that may be compromised. Okay, when the robot is accelerating fast, the payload should be less than the maximum mass. So this is affected by the ability to firmly grip the part as well as the robot structure and the actuator. The end of arm tooling should be considered part of the payload. Then settling time. So during a movement, the robot moves fast, but as the robot approaches the final position, it slows down. Okay, this thing we also observe in the programming. Okay, between the endpoints, the movement is fast, and near the endpoint, the movement is slow. The setting time is the time required for the robot to be within a given distance from the final position. Okay, here the coordinates they are shown X, Y, Z. Because the robot can move, therefore it is necessary to define the positions from which position it has to move to which position, initial position and final position. So the coordinates here of the joints that are shown here in the XYZ domain. Okay, so tool coordinates, then joint coordinates. Both are there. Tool coordinates with orientation that is considered, and the tool coordinates are measured against the frame attached to the tool. Next is the joint coordinates. The position that is theta 1, theta 2, theta 3 means how much the joint that is moving. So now coming to accuracy and repeatability. Okay, and the resolution and that is the use of digital systems. Again, other factors mean that only a limited number of positions are available. Okay, thus the input coordinates are often adjusted to the nearest discrete position because there are limitations in assigning the or determining the exact location and then assigning the location as a position to the robot. Okay, then kinematic modeling error. The kinematic model of the robot does not exactly match the robot. As a result, the calculations of required joint angle contain a small error. Okay, next is calibration error. The position determined during calibration may be off slightly. It means the position which we have determined, that is not the exact position of the object or of the tool. Okay, so there is an error. So that is a calibration error. Okay, then random errors. So they are due to the problems, okay, due to the operation of the robot. They are occurring. Okay, some examples are due to friction, structural bending, thermal expansion, backlash. Okay, this type of errors. Then accuracy. Accuracy determines how close the robot gets to the desired point. This measures the distance between the specified position and the actual position of the robot and effector. The accuracy is more important when performing offline programming because absolute coordinates are used. Okay, next thing is the repeatability. So this is that how close the robot comes to the position, one position again. Okay, means once it has moved to a position and then it has to come back to the same position. So repeatability means it will come back to the same position any number of times. Okay, otherwise there could be some deviation. It moved from a point A to point B, then it is coming back to point A. Okay, so repeatability is high, so it will come exactly at point A. If the repeatability that is low, then it will not come exactly at point A. It will come nearby point A. Again, this will go on increasing because it has to perform same task a number of times. Okay, so a measure of the error or variability when repeatedly reaching for a single position, that is the repeatability. This is the result of random errors only. Repeatability is often smaller than accuracy. Next is control resolution. So spatial resolution and control resolution. Here, spatial resolution is the smallest increment of movement into which the robot can divide its work volume. So smallest increment in the work volume. That is a spatial resolution. It depends on the system control resolution and the robot's mechanical inaccuracy. So it's easy to conceptualize these factors in terms of a robot with 1 degree of freedom. Because the next is control resolution. It is determined by the robot's position control system and its feedback measurement system. So feedback system, something in the basic system we studied that was using the sensor. Okay, so position control system and the feedback system. So it is the controller's ability to divide the total range of movement for the particular joint into individual increments that can be addressed in the controller. So the increments are sometimes referred to as addressable parts. The ability to divide the joint range into increments depends on the bit storage capability in the controlled memory. So mechanical accuracies, if we neglect them, then accuracy is equal to control resolution divided by 2, means half of the control resolution.